Okay. Good morning to this webinar. The UPC Global company is giving to you today. And the topic that we are going to cover today is enriched inflow performance relationship curves for simultaneous selection of target rate and pump setting depth while visualizing free gas conditions. Mr. Caicedo, he's going to give the presentation. Just 1 minute. He's going to give the presentation, and let me introduce you Mr. Caicedo. He holds a bachelor degree in physics and computer science from Simón Bolívar University, Venezuela, as well as a master petroleum engineering from the University of Texas at Austin. He has 27 years of experience as a specialist in artificial lift, well productivity, and software development applied to oil production. He also has worked as an instructor in oil production, where he has trained about 700 plus engineers in the companies where he has worked. He has published around 30 technical papers, and Mr. Caicedo has worked as a specialist in artificial lifting in Venezuela, Kuwait, the United Arab Emirates, and the United States. He was awarded with the SPE Middle East Production and Operations Award in 2015 for his technical contributions in artificial lift, and he is the academic director of the UPC Academy. Thank you, Sergio, for your time, and you can start your presentation.
Okay, good morning, everybody. Before giving the technical presentation, I'm going to give a short introduction about UPC Global. We are experts in artificial lift. Who we are? We are a lean consulting company that offers strategic solutions in the area of artificial lift and production optimization. We supply hardware and software and provide training oriented to analyze, optimize the well performance. Our mission is to satisfy customers by providing technical solutions for the oil and industrial sector. We guarantee exclusive alliances with leading technology companies while offering high-quality service, supported by an experienced team of specialists in each area. Our vision is to become worldwide recognized leaders in the oil production business, always guaranteeing high health, safety, and environmental standards for our employees and operations. Our service, we provide field data acquisition, optimization, analysis, and elaboration of production plan, specialized trainings, presentation, and online academy. I'm going to explain you right now, telemetry and automation. So, online academy, become an artificial lift certified experts. You can you can access this web page over here. You can find it in type it in Google and find it. This academy has access to 20 hours, 365 days, 40 hours estimated hard work, 2 months to finish each course. Right now we have available release, no analysis, gas lift, computer fundamentals. Soon we are going to provide ESP, intermittent gas lift, cycle stream injection with artificial lift, fluid levels, and dynamometer cards. The course consists of video classes, with classes and real exercise in Excel and a computer. Besides of the videos, there are video conference for clarification sessions. At the end, you are going to present an exam online, and you are going to get your certificate for each course. So, as you can see, we have worked with many customers and have done many alliances with very recognized companies. So let's talk about the today webinar. We are going to give a brief introduction. We are going to give a theoretical background. We're going to talk about the enriched inflow performance relationship, EIPR concept, the sensitivity case, other possible attributes and display formats, conclusion and recommendations. So at some time of the life of the well, you are going to require artificial lift because the well produce production, and you want to even to cease to produce, and then you want to increase. There are two artificial lift big branches, pumping method and gas lift method. Even when pumping represents 75% of population of the wells, the pump setting depth procedure has not been clearly determined, and the gas percent of gas into the pump not clearly understood. The pumping method will have electro-submersible pump, progressive cavity pump, socket rod pump, jet pump. And even they have different working principles, there are common problems when designing any of these methods. The reservoir inflow performance will be considered. Free gas effect in different has different effects in each method. Free gas has different limits in each method. The pump setting bed must be defined. The pump setting bed, the target rate, and the free gas are interrelated. There is a trade-off related to the setting depth. Okay, so socket rod pumping, we have a reciprocating pumping piston at the bottom, a unit at the surface. We are talking about 10 strokes per minute, revolution per minute at the surface. We have two valves, the standing and the traveling. This open by compression. And we have a static downhole separator, 30 to 70%, depending on the case, depending on the size of the casing and the size of the pump. The progressive cavity pump, downhole, is rotating the rod. We're talking about 250 RPM. It's a positive displacement pump. We have elastometric stator and metallic rotor. We have a tight contact rotor stator that is affected by the free gas. That's why it requires lubrication, and the stresses should be distributed along the pump. All this in red is affected by the free gas. Also, we have a static separator here. We have the ESP. Here we are talking about 3,600 RPM, very fast. Talking about multi-stages centrifugal pumps. And we have a rotary separator at the bottom, which has 80 to 90% downhole gas separation efficiency. We have jet pump, high pressure pump, and facility to separate liquid at the surface at the wellhead. We have a downhole jet pump. The idea it transfer liquids pressure by momentum transfer from the formation from the power fluid to the formation. Okay, there are no moving parts in this one. We have to use a Parker, so no gas separation at the bottom, 0% of efficiency. What is the depth trade-off? Well, the deeper the pump, the lower the free gas into the pump. We are going to see this. The deeper the pump, the higher the maximum rate that could be produced. The deeper the pump, the higher the temperature, which is not good. That's why it's in red. The deeper the pump, the higher the cost. The deeper the pump, the higher the risk, especially in horizontal wells because of the dogleg severity and failures. The deeper the pump, the higher the rock weight and stresses, PCPs of the rock pumping. This talk is going to deal with all of them. This is a general. Essential concept to keep in mind. First point to highlight in artificial lift pumping is that the real problem is the free gas percentage that actually is passing through the pump after downhole separation, if you have any. The free gas into the pond is affected mainly by 5 parameters: the gas oil ratio, UR, pond intake pressure, bubble point pressure, water column, and downhole separation, if any. The problem is not only GOR. People think that high GOR wells, then I cannot work. Low GOR wells, I can work. So it's not only GOR. You are going to see later that a high GOR with a high pressure could work, and a low GOR with a low pressure could work. So do not confuse gas handlers. Please handle capacity with gas separators. That is different. That is the separator capacity. By the way, we could use both simultaneously. I could use a gas handler with a gas separator. They are different. The free gas effects. The first point is that the gas dissipates, which requires higher pumping capability. For example, if you want to produce 2,000 barrels and you have 50% of free gas, so the pump has to be sized for 4,000 barrels. Regardless of being an ESP, PCP, or whatever, doesn't matter. You know that 50% of the 4,000 is going to be used by the gas, so in reality, you are going to be able to produce 2,000. In addition, each method has its own free gas limit and effects. So if we have ESP, radial flow impeller, 10% of limit. If we have ESP mid flow, 20%. If we have ESP gas handler, 40. If we have ISP axial flow, we have 70. And the effects in the ESP are you are going to have gas lock. When you have gas lock, you have to trip your pump. Otherwise, you are going to burn the motor because it's going to overheat the motor. If you do a trip, then you are going to have a low production and low efficiency. Okay? PCP, normal 40, elastomer is going to overheat, high pressure, shorter burn life. Not going to have a gas lock, by the way. The hydraulic regulated PCP, the limit is higher, the same problems, so you're changing the limit. Socket rod pump, probably you can 50%, probably above that, 70. You can produce, but you're going to see a lot of inefficiencies in the problem. Lower, you are going to have a lower compression radio, temporary gas lock, energy waste, low production. Okay, so and when you have jet pump, the problem is that you are going to require high volume of production, the power fluid, and higher pressures to overcome this problem. So always you have effects of the free gas in your pumping. So the first thing we are going to see, the deeper the pump, the lower the free gas. Remember that trade-off. So pay attention to this case. The bottom hole full pressure, 3,000. We are operating at this point because the pump is far from the formation. Here we are 10,000 feet. So for this setting depth, for when you have 3,000 psi at the bottom, you are going to have 1,000 psi at the intake and 20% of free gas. Here I am expressing the gas system of barrel per day. I change the units from the standard cubic feet to have an idea how much is that using same volume units. And the temperature is not so high. If I, for the same case, pay attention, the same production rate, but deeper setting depth. For the same condition, I'm going to have higher intake pressure, higher temperature. The high intake pressure is good because I have less gas and I have less gas rate, as you can see. But I have to go deeper. Let's see what happened with the maximum rate you can produce. If I have a shallow pump, the maximum rate I can have is having the intake pressure. I'm going to have just as theoretical curve, this type 0 psi, which is not reality, but I'm just showing you you are to the limit. You cannot have negative pressure. So you cannot produce, when you have the liquid fluid level here and the casing pressure in 0, that's the maximum you can produce at with the pump at this depth. You have a lot of free gas, you can see huge quantity, a lot for this, and the maximum you can get is when you have 0 pressure here, the bottom hole fluid pressure is to be 2000 psi for this distance. So this is the inflow curve referred to the pump intake. Okay, so the maximum is this. So I don't care if the reservoir can give you more, just because of the setting depth, you cannot produce more than this rate. Okay, the deeper you install, then you use the same condition, 0 pressure the intake, just to explain the concept. Then I can reduce the bottom hole more, so I can produce more. You can see that now that this intake, the inflow performance curve referred to the pump intake, has higher maximum rate here compared with the previous one. The red lines, you see, I can produce more just because of the setting depth. So that's why I want to go deeper, but then the price and the temperatures increases, which is not good. For example, temperatures for the elastomers is not a good idea, high temperatures. So regardless of the artificial pumping method, you're going to see that all the software, they request the pump setting depth as an input. So you start guessing. People start with a given depth, providing information from the completion, and they select a target rate for the IPR. Then they calculate the intake conditions, they select the pump, and they select the pump and other component, and they ask and check if it's possible or not. It is possible. Many people stop the design here, but first question, is feasible, but maybe I can get a better design. Can the pump rate be increased? How much? Or can the pump be installed shallower? How much? So that is something you have to realize, that even you find a feasible design, there are 2 questions that still you can improve in your design if you are able to answer these questions. When the design is not feasible, then you have to guess. Can the target rate be decreased? How much? Can the pump be installed deeper? How much? And take another guess and continue until you get a feasible condition, if you can find one. Okay? This is procedure time consuming that depends on the artificial lift engineer experience scale to find a solution, if any. There is no visualization of the situation when you are doing this design by try and error. Okay? Then let's compare the way that the pump softwares work. They request result data, completion PVT data, production rates, the target rate, and then the pump setting data is the input data, and then in the output data, suitable system specification, pump models, name, ESP, operational condition, whatever. And then free gas into the pump is an output. But if we compare with what happened when you're doing a gas lift design, you're going to see that it's very similar. The target rate is sometimes here, and sometimes the system tells you of the maximum. But in the output is the mandrel depth. You can see here. Meanwhile, in the pumps methods, the setting depth of an input. So I would like to have the pump setting depth as an output and the free gas percentage, your limit of your pump, as an input. And that will change the traditional way to design ESP, PCP, soccer rod, jet pumps. Okay? So how the completion affects when you have no packer, then you have a separator, this gas at the intake of the pump, then the separator send some of there are some gas that by natural separation, it doesn't come into the gas separator. The gas that comes to separator, most of them is expelled to the annulus, and some part comes into the pump. That is the problem. When you have downhole separator, you cannot use a separator with the packer because you have to handle all the gas. This situation happens when you have H2S to high levels and you have HECE restrictions. This is one condition that happened in the Middle East. So in this case, separation efficiency is 0. Everything has to be handled through the pump, unless you have a special completion, dual completion, that the gas goes through another tubing. But in general, this is the case when you have packers. But worldwide, most common completion is without packers. So as I told you, the highlighted bubbles in yellow is the problem. The gas that is going through annulus, and it's not a problem at all. The problem is the highlighted. So the free gas pump definition. The free gas is the quantity of gas divided by the quantity of rate of gas, oil, and water at the pump intake condition, pressure and temperature. That is the definition. Okay? So gas divided by gas plus oil plus water. By the way, doing recirculation or injecting external water to the bottom hole can reduce the free gas, as you can see from the equation. So the gas that comes into the pump is the gas that arrives to the intake from the reservoir, taken away by what is taken away by the separation. So if you have 100% of efficiency, 1 minus 1 is 0, you have no free gas, but that is not the real case. If you use this equation and we use the gas from the reservoir of the oil rate times the UR minus the solution gas, because UR is measured at the surface, but the solution gas is what is in solution at that pressure. Okay? If the solution gas is equal to the UR, you also have no gas, 0. Okay? We're going to see this in a table right now. The separation efficiency is the natural separation and with the separation device. It considers both. By the way, you are not adding arithmetic, and this plus means we are using both. You are not going to add separation efficiency, by the way. By this equation, we are going to see that we can type the water as oil with the fraction. We have the writing the gas as oil times UR, essentially, and then this expression vanishes, and we have an expression that depends on the following variables. Pay attention that the solution gas helps. The higher this number is better for the pump. The final step is to introduce the gas equation into this expression, and then we have the equation for the free gas, which is this one. So pay attention that we have to pay, this equation depends on the intake pressure, intake temperature, bubble point pressure, solution gas, percentage of water, and separation efficiency. Therefore, you require a good knowledge of PVT to predict the solution gas at the pump intake conditions. Requires good knowledge of the downhole separation efficiency model. Requires good knowledge of downhole separation efficiency. So using a low value, you are going to be conservative. You can use Alanati models. Most of the models tested with lab data shows that the separation efficiency decreases when having high rates due to the liquid dragging, and the separation efficiency changes for each method. Okay, so keep an eye on this. The result must be compared with the artificial limit of the pumping system. Once I got this number, if they give me 30%, then I compare with my method. It is PCP, no problem. Is it ISP with radial impeller, then I am in trouble because it exceeds that value. To avoid surprises, let me show you tables to see how this equation behaves, to understand some important points here. Here I have 6 tables. In the columns, we have different intake pressures. In the row, we have different all ratios, okay? And the water is increased from left to right. And in the top, we have no separator. In the bottom, we have separator. 0% separator, 80% separator. Just to see the effects, and you will see something interesting. First of all, you can see that there is 0 gas in this condition. Why is that? Because we are above the bubble point. Just to show you how important is the intake pressure. If you are above the bubble point pressure, there is no free gas, regardless how big is the UR. Okay? This is the best, the first important point, how with the bubble point. Second, let's see what happened with the water. So you are going to see how the water helps. Let's compare this corner here. So 400 PARP and 3000 UR. 96%, 92, and 55. Let's see, that is with no separation. Let's see with 80%. We have 82, 70, and 20. And in the corner, no, let's see something in between. You have to compare the equivalent cells to see the effects of the value we are highlighting. Okay? So water increases, then the free gas decreases. That is the first thing you have to notice, and we knew that from the equation because the water was dividing in the fraction. Let's see with the separator. Having no separation and separation. So let's compare this corner, 96 against 82, 92 against 70, 55 against 20. So the gas separator helps. Let's see what happens when you have a fixed intake pressure. For a fixed intake pressure, the higher the you are, the higher the gas, the free gas. We know that. So this is to highlight that this is the only variable that people have in mind. Yes, I know that when UR increases, for a fixed pressure, it will increase, but take care with the other variables, okay? And then the most important, let's see what happened with the intake pressure. Look that having, for example, let's compare here. I highlighting in each table 3000 UR with 400 PI, 3000 UR with 2800 PIP against 450 UR and 400 PIP. You are going to see that this case is worse than this. 400 PIP with 450 UR has more free gas than 3000 with 2800. Pay attention here, the same. We have here 70, 75, 57 against 61, 13 against 14, 31 against 38, 21 against 24, 3 against essentially 2.9, something like that. So take care, because sometimes people think, I have a low UR, I can work. What is your intake pressure? Take care with this. Not a good rule just to think in terms of UR. People it's not considering the method, because I have high UR. What is your pressure? Maybe you can work, and it's considering it's possible because the UR is low. What is your pressure? It's too low. Maybe you are going to have a problem. Okay. So, what's the traditional tool to select the target rate? When you use any of this software, people start considering the inflow performance at the perforations with no artificial lift consideration. So this is my inflow. I'm greedy. I want to get a lot of, and then I select a rate, whatever it is. So the point is, it is feasible. I can increase my rate, or I cannot go so high, or I have to reduce. I don't know. And then some programs after design show the EIPR at the pump intake.
Sorry, Mr. Sergio. Sorry.
Yes. So depending on the position, and we cannot be sure, because we're going to start, most of the software that do it, they're going to start try and error, because we don't know. We only using the intake, the inflow performance at pump intake. Questions are at the very end. So what is the idea? The first step to reach our goal is to plot the EIPR at different setting depths. So this is the EIPR. The continuous line is at the perforations. In this case, at 10,000 feet, 8,000, 10,000, 9,000, 8,000, 7,000, and 6,000. Different colors. Even I did something 1,000 feet deeper than the reservoir, just to explain a concept. Okay. So what you're going to see here is that I have not setting that decision have been taken at this time. Just plotting the inflow performance at different depths. Okay, so this inflow performance at different depths provide me the intake pressure and temperature at the intake. So I can use these values to be introduced in the equation. And then I also see the rates. So, but still spending the free gas to be displayed. So what we're going to do, we are going to plot the inflow performance at different depths. And then I'm going to add points with a color scale to these inflows. So this is the idea. Here is the same inflow, but now the concept is to add the points with colors. So what is this? The black color, for example, tell you 0 to 1% of free gas. You can see that if you are below perforations, that helps a lot in the separation. You have 90 something, 95, 98% of separation efficiency, maybe 100. Then blue points are dark 1 to 5, light blue 5 to 10, green 10 to 15, yellow 15 to 20, this dark, this orange 30 to 40, and so on. And then I can visualize the product when doing my design. So let's see here. What happened here is I have a very high separation, so I can go, if you are below the perforation, you can produce from the gas point of view almost all the potential of the well. Okay? And this EIPR not only provides information to do the right design and select and visualizing, but instead of guessing, I can use this as a new way to do the selection. Let's explain this. Let's start with the approach is starting with a free gas that you are selecting as an input parameter. So let's say that we select 10% of free gas. I don't want to have more than 10% of free gas because I'm going to have ESP with radial impellers or whatever. 10% is my limit. I fixed that as an input. So that tells you the options are going below perforation is one, but then you are going to have another problem with this. Or you can see I can go to the produce almost everything. This is one option, but that will bring you more temperature, heating, and so on. Talking about free gas. I can be at perforation at 10,000 feet, and the maximum rate I can produce is this quantity, this 3,500. Or I can be 9 feet with 1 feet above 1,000 feet above perforation. Maximum is 3,000. Or I can go 2,000 barrels at 8,000 feet. Or I can produce 1,200 barrels at 7,000 feet, 3,000 feet above perforation. But if I install at 6,000 feet, I cannot produce because at the time I start producing, I'm going to have more than 10% of free gas. So immediately with this graph, you are seeing setting depth, rate, feasible rate, and free gas values. And also you can see the tendency is clear. The higher the rate for a given depth, the higher the rate, the lower the PIP, the intake pressure, and the higher the free gas, because as I explained you in the tables. You are going to see the shallower is the pump, the more difficult becomes to be the problem of free gas. Okay, what happened with the black here is for this case the bubble point pressure is 3,000. So as soon as I am about 3,000, there is no free gas into the pump. If the 3,000 is the intake pressure of that rate, okay, and so on. So if you have a capacity to handle 40%, so it will be for the free gas will be the orange, okay? And you are going to see, for example, let's see that your capacity is, let's say, 50% the green. So it will tell you, and suppose that for some reason, reservoir people don't want to produce more than 4,000 barrels, okay? So because you can create water coning or sulfur facility, they cannot handle more production because the facilities are to the limit. So for 4,000 barrels, if you have capacity to handle 50% of free gas, then they're going to see, I can install at 8,000 feet. I don't have to install at the bottom hole because at 8,000 feet, and I'm going to have for 4,000 barrels, that is my limit, because the restriction from reservoir facility people, I can handle that production. I don't have to go so deep. So it's a new approach that allows you, and besides, it's going to tell you when talking with reservoir people and other people in the team, what is your real chances. So with these graphs, you can have a meeting and everyone is going to understand what are the possibilities in your design. So this EIPR course provides easy content to explain and communicate with no artificial lift specialists, and explained it before with colors is the easiest way to understand this. You can talk with the reservoir engineer, fissile maximum rate, completion engineers, packer effects, green engineer effects on frustration in depths. So if the line is too close to surface, you are going to have a problem. The rat holes, the trajectories. So you can see it with everybody to talk about your well, and everybody's going to understand the problem. So let's see what happened with this curve doing some sensitivity case. The base case is GOR 1500, water cut 50%, separation efficiency 70, reservoir pressure 4,000, productivity index 3 barrels per day per PSI, and bubble point 3,000 PSI. I'm going to decrease the GOR. I'm going to we're going to reduce the separation efficiency. The reservoir pressure I'm going to decrease, and the productivity index I'm going to decrease. I'm going to do one change per case to see what's doing each parameter. So GOR and water. Here is our reference. And you're going to see what happened with the 1500 standard cubic feet. It's very difficult in this case down here. 1500 with no separation. With we're going to see here that what was initially feasible no longer is feasible. It's very, you're going to have a lot of gas. The GOR is creating problems. There is no water. In this case, this water, 90% of water. So even with 90% of water, I can work even having 1500 standard cubic feet per barrel. So it's important to see the effect of GOR and water on this. Yes, GOR affects, but pressure and water also affects. So keep that in mind with this graph. Let's see what happened changing the reservoir pressure. Here, at the top, we are going to see that we reduce the productivity index from 3 to 1.5. So if you are working, if your design was to work in this range that I have highlighted here, when you change the productivity index, you are going to see here. So what was to be very easy case now is very difficult case. The same happened with the reservoir pressure. If I reduce the reservoir pressure, then what was a feasible area, 10% maximum, then no longer is 10% maximum. It's going to be very difficult to produce. Okay, let's see about separation efficiency. Here I have 70% of separation efficiency. Here I have no separation because I have to install packers, because H2S restrictions, integrity issues. Then that has a price. The price is that you are going to have a lot of gas. And here, we are going to see what happened here is, in this case, the efficiency is high at low rates in the bottom and low at high rates. You are going to see that at low rates, these blue points move, as you can see here. This green is now blue. You can see some points that change a lot. And here, the red moves, and then you have problems because at high rates, the separation efficiency decrease a lot. Take care of that. It's not a constant value. The separation depends on the rate. That's why I told you you need to have a clear understanding of the separation efficiency. So we can use this idea to provide a tool to visualize the target rate, setting a free gas into the pump. But we can extend to visualize total rate into the pump, which is the oil rate, the water, and the remaining gas. And we can have the horsepower to providing information that is very important for artificial lift, is to know if you are going to have restriction in the HP available. We can now also add information as another idea is having, you have another problem of, for example, asphaltene are very sensitive to pressure. This idea could be used for that also. So here, total downhole rate, you are going to see how it changes the total downhole rates here, how much rate you are going to handle in the pump, which is not the same the surface rate. Okay, you are going to see here that, for example, for 3,000, in reality, you are going to handle 3,200 to 4,800. Because this is in the inflow, this is standard condition, but at the bottom you have total rate. If I don't have downhole separation, you are going to see I have a lot of total downhole rate, and this is important to have an idea about the size of the pump. As I explained you at the very beginning. Let's see, with the horsepower is the same. I can have an idea how much horsepower I'm going to use to have an idea of the equipment I'm going to use. And also you're going to see the higher the rate, the higher the HP I need to install in the motor. Conclusions. The EIPR concept is innovative, useful, and feasible idea that allows the simultaneous selection of target rate and pump setting depth while visualizing free gas and reservoir condition. That applies for ESP, soccer rock, PCP, and the pump doesn't. It applies for all these methods. The EIPR curve allows and proposes a new approach to design pumping method that started with the free gas pumping capacity and then selected the physical production rate and corresponding pump setting depth. The EIPR can be extended to show other parameters such as the total downhole rate and estimated power that complement the initial objective of displaying simultaneous free gas percentage. The EIPR course provides an easy concept and tool to explain and communicate with non-artificial lift specialists about the target, pump setting depth, and free gas condition, as well as other parameters such as the total rate and estimated power. Recommendations: use this EIPR course to communicate with other specialists. Since the plot IPR color scale requires intensive computation, that is recommended to the artificial lift engineer to develop on software or to request software providers to develop this feature in the program at the design stage rather than the output stage. The EIPR is sensitive to some parameters that is recommended that when having uncertainties on reservoir pressure, productivity index, water cup, the peripheral efficiency are low, the lower values should be taken to have a conservative design. So you need to do sensitivities. So just with this, I finished the presentation. Just news for you. We have no analysis course online. We have a promo code here that is valid until April 9th. 30 coupons are available. Okay, so we are going to have a discount with this online course. Take advantage of this. So, same for your valuable time annotation. If there is any question, please feel free to ask.
Thank you very much. Thank you very much, Sergio, for your information. And as you say before, I'm sending through the chat the link to our academy. So I invite you to visit there. And you have information about the nodal analysis course also. And as you mentioned before, we have a promotion code. And if you can, please, can you come back to the last slide in order that people can take maybe a print screen of that promotion code and you can use it if you decided to take that course. So if you have any question, please now you can make it. So if someone want to open his the microphone, it is possible to do at this time also. I think that Luis have a question or comment. I'm not sure. Luis, can you hear me?
It's just that I have some problem with Mr. Sergio was talking about. Hello, Mr. Sergio, how are you?
Hi, how are you, Luis?
It's nice to see you again.
Same to me.
Mr. Question, I just had two questions, especially in the correlation that you perform. It's basically about the temperature. Can you go to that slide, please?
This one.
Or
This one.
yes, there. My question is, what is the effect of the temperature on that correlation? Because I
Okay,
had
okay,
to
okay,
do.
okay. Remember, let me explain you with this. This is a pump intake pressure. When, for
Yeah.
example, when you have, let me give it in a very fast way. Okay, when you have, for example, your standard. Remember that the GOR units is standard cubic feet per standard bar. Standard cubic feet, that is a 14.7 psi and 60 Fahrenheit degrees. So if you have 1,000, if you have 100 at 14.7, at 147 you have 10 times the pressure. So the volume is not going to be 100, it's going to be 10 standard cubic feet per barrel at that location. And then the other correction you have to do is temperature, okay? Because the gas equation affects. So what happens is when you evaluate this is just the equation of the state. Pressure times volume is equal to number of molecules R, compressivity factor, temperature. So what happened is that this 520 is 460 plus 60 because this is in ranking. Okay?
Mm-hmm.
So when you have 60 degrees, this value is 1. It's not, there is no correction by. So by temperature, if you have to have very high temperature to see a change in this, because this, what happens is because it's ranking, you are adding 460. So if you have 150, you are going to have this value is going to give you, let me give you an idea how much is the correction factor for this. Let me open one calculator here. It's going to give you, to answer your question, 160 plus 150 equal 1.70% more. Okay, that is the point. Hello, it's clear. That is the effect of the temperature. It's okay. Yes.
Yeah. It's just no. It's just when you have there are some issues with my audio. Okay, perfect. So, Mr. Sergio, it it means that if I adjust that temperature, I have to do the same for the the solution gas. I also have to adjust that temperature, or I can just
Yes.
use
No.
what we
No.
have in
No.
the PVT.
No. You have to have your PVT core very good. So the recommendation is go to the reservoir guys, get the PVT data of that reservoir, because that is a table. Okay, that is one of the. In fact, this
Okay,
slide,
perfect.
that is
Understood.
here, that is exactly the message. Why I have 0 here? Because at that pressure above the bubble point, the solution gas is equal to the GOR. If you have not a free, let's suppose that you are in not a free gas. Usually, if your reservoir is below the bubble point, you don't have a solution. You don't have a gas cap. Remember, when you have a gas cap, then the GOR, if you don't have a gas cap in the reservoir, the GOR should be always equal to the solution gas, at the bubble point. Okay, should be flat. Okay, and then you have to take away this. When you have a gas cap, the GOR is much higher the solution gas initial conditions. But yes, you have to take, if you don't do this, the number is going to be wrong. By sure, you have to do it. That's why you have deep knowledge of the PVT. You see? At that pressure and that temperature. Yes. Okay?
Okay. So,
any other questions? Because I remember someone tried to add something in this graph, I guess. Like someone was trying to add something here, I guess.
I think that was Luis. I'm not sure. But just to make a comment, Alberto mentioned that he suggests that we can have a webinar in Spanish. So I told him that we already have. I'm not remember if we have a record of that, but
yes, we have.
Yes,
we
have it. Yeah, so we can send to you this version also, Alberto, and in order that people who speak Spanish or native language is Spanish can have that information also. So let me know if you want it, and for sure we'll send to you.
And the reason we are talking in English right now is that this is for people who speak English. So otherwise I will ask you in Spanish, but the idea is that question and answer remain in English, so everybody can access to this video when it's posted in our webpage. And then if you want to see it in Spanish, it's there, I'm sure.
Perfect. So if anybody have a question.
Good morning. I have a question. The principal idea of EIPR concept is to
visualize rate, depth, and free gas at the same time in this graph. That is the idea.
Okay, but always is being through the software.
Okay, let me explain you something. To do this, I developed my own software because there is no commercial software to do this. Okay, I have this. This is my own software for this. The colors and the points are given by the software, but there is no commercial software that do this. In fact, they don't even pay attention to this concepts being so important. Okay, what I am telling you now is when you are doing a design with a commercial software, whatever system you want, PCP, soccer, keep this in mind, because the problem is that you don't know what is happening. So I have free gas. What I'm going to do, for example, let's talk about operations. If you are in operations and I have free gas, what I'm going to do I have free gas, reduce the pumping speed, because for that depth and that separation, that is the free gas and period. The setting depth is given. Once that you install is there, there's just one core, and the only solution clearly is to reduce the pumping speed to reduce the free gas. There is no other solution, as you can see now. And when you are designing, then you know, oh, if I have too much free gas solution, trying to install deeper, try to reduce the target rate, then this is the option. So this gives you an idea of what to do. For a specific value, then I can run my software for you and give you this is your case. Okay?
Okay. Yep.
Okay. I think that we have no more questions. Let me check just a moment. No questions? Okay. So Sergio, can you go to the last slide, please, to show again the information about the nodal analysis? I want to mention that UPC Academy is a new concept that we offer. We are artificial lift experts and we have in-company courses, but now we have online options. And in these times, it's a good alternative or a good option to consider in order to become expert in artificial lifts and also to have certifications about that. This academy is think about have online videos and in material that you can check, and we also have online sessions with the instructors. In that case, Sergio is one of them, of course. Give me one moment.
Right now, under this coronavirus condition, having online courses is very important. And even later, companies with the oil prices, restriction to travel probably, so online courses are going to be a very good option to get training, okay?
Fine. Finally, Sergio, Luis is telling me that he couldn't listen your last answer. So I don't know if you can repeat it, or maybe you can to write this answer and send them that information. I don't know.
Which answer was the question? I can't remember the one.
The last question that the last participant Rojas Acosta made about the
okay.
Yeah.
Okay. This course are not offered by any. There is no commercial software that do this. I program my own software to do this. This point here is not a PowerPoint presentation, let me tell you. I can show you the Excel that makes the computation to provide you the colors that you are seeing here. So this program I give the GOR, setting the productivity index, all the parameters as any other software. And the output of that program is this course. So you can tell the depths that you want to see, this depth, a set of depths, just to see the tendency. And then the program output is going to be this. With this, then you can make them have an idea what's going to be your case in your software. Then once that you have this guide, then you go to the software and say, I know I'm going to, once that you have this, I'm going to say, okay, I'm going to produce, I'm going to set the setting depth 9,000 feet and the rate 3,000. And you're going to see, when you're doing your design, I'm going to tell you 10% of free gas because you knew the solution. You don't have to be guessing anymore. Okay? But it's a software. Okay?
Okay. Okay, Sergio, so I think that we finished this webinar for today. I want to thank you everyone for being here, and it's just an opportunity to share information, to learn about your experience. And finally, I want to give you thank you and have a nice day. Thank you, Sergio, for your time again, and we'll see you. I think next month.
Okay. See you. Take care of your health. And see you soon in our next seminar. Have a nice day. Bye.
Bye. Thank you.